Okay, I think we'll get started. Thank you all for joining us this year for the ROCKE-3D tutorial. We've already sent the schedule ahead of time, so hopefully you'll all have seen that, but I'll go through it here in a couple of slides. And today we'll be joined by Kostas Sigouridis and Igor Alienov, who will also be chatting some up today, and Anthony Laboisetier. So let me share my screen. If you have any questions, please address them in the chat window. Unfortunately, because of my small screen, I won't be able to see the chat window, so I'll leave it to Kostas and Igor to relay those if anything's needed. Okay, so here we go. So you can see a number of people are involved in the tutorial over the next 2 days, and each of these people have been involved in some aspects of the model development or usage for the most part. And as we say here on the first page, we have links to previous years' videos of the model. They're almost all the same, probably. Maybe we've gotten a little bit better and maybe some ways worse, I'm not sure. But this year's tutorial will also be posted online after the tutorial is done. As we said before, please keep yourselves muted and your video off. And if there are any problems, please email one of us during the tutorial presentation. Of course, we won't be able to reply to your emails if it's one of us presenting, as you might imagine. And this is our rough schedule for today, which hopefully you'll all seen. This is the same in the first email I sent out about the tutorial. So myself and Kostas will talk in these first 45 minutes, roughly. We'll have a 15-minute break. We'll have another 45 minutes. We'll have a good lunch break. Tomorrow we only have an hour, but today we have an hour and 15 minutes. And then again in the afternoon, and we'll have a break. And then we'll just have a general question and answer at the end for those of you interested in chatting. You don't have to stay for that. It's completely up to you. If there are things that you don't understand that we described, then that is the time to ask those things rather than waiting until a week after the tutorial when you've forgotten some of the stuff you might have learned from us. And this is the schedule for tomorrow, which I'll talk about again tomorrow. So I thought I just should mention very briefly a few things about these global circulation models. There are different kinds of global circulation models. You might imagine they're very simplified versions of these. There's 1D models, there's simplified 3D models like PLASM, and then there's these full-blown 3D, three-dimensional general circulation models like we're talking about today for this tutorial, the ROCKE-3D. They're very complex, as you might imagine, which is why we have to host such a tutorial to make sure that people understand how the model is run and what its limitations are. So you can see here, first of all, timescales for simulations are up to around 10,000 years. Those are model years so far. We haven't run much longer than that. It's basically just because it takes the model a long time to run that number of years. And by years, of course, I mean Earth years. If you run, say, 10,000 Earth years with our standard 4x5 model, which we'll talk about what 4x5 means, that's the latitude and longitude degree size. That can be 6 months or a year of running, depending on different factors. The vertical range, at least for the top, goes up to about 65 kilometers. We cannot simulate atmospheric escape. People are always interested in that topic, but not with our particular model. And you can only get mixing ratios, as we say, in the stratosphere. And we're limited to shallow atmospheres. What do we mean by shallow atmospheres? That means that the depth of the atmosphere, the scale height of the atmosphere, is small compared to the radius of the planet. So we cannot do things like many Neptunes. And we even have difficulty doing Titan, although we have done very little Titan work with this model thus far, although we have ambitions to do some Titan simulations down the road. But the validity of the model becomes a bit shortened as the scale height of the atmosphere approaches the radius of the planet. And this is kind of an overview of what these 3D GCMs sort of look like. This is, of course, a cartoon diagram. Don't take it too literally, but there is sort of a coupler that brings in the different aspects of the model, the atmospheric part of the model itself. This is a coupled ocean atmosphere model. So we have an ocean component that talks to the atmosphere. We have land ice and sea ice, as you see here. And we also, of course, have a land component, which involves even vegetation, but really restricted at the moment to modern day Earth type vegetation if you're interested in looking at such things. I thought I would just review a few things that the model is good for. First of all, I would just mention that we do have a model description paper with an incredibly long title, as you can see here. And that's really the first resource that you want to go to if you have questions about the model and what it can do and what it might not be able to do. We try to document as much as possible in this model description paper, which I led a few years ago. There will be a second iteration of ROCKE-3D coming out, hopefully in the next few months. We were hoping to have it released last year, but we ran into some issues with the ocean components, which have been resolved. And we're just doing some final checks on the current 2.0 version of ROCKE-3D. And that paper we're in the process of writing as we speak, which will again document the model in some detail. And that will be led by Kostas Sigouridis, who will talk later today. So with this model, we've modeled a number of atmospheres. Traditionally, the parent Earth climate model, which we call Model E, was used to do paleoclimate studies for quite a long time. And we do discuss some of those in various publications, including in the GCM description paper, but also in this 2018 paper led by Tony Del Genio, where we look at Earth through time, going all the way back to the Archean about 3 years ago. We've also looked at hypothetical scenarios. For example, Venus, this is probably one of our more popularly cited papers, was Venus the first habitable world of our solar system, where we look at the probability that Venus could have had a habitable period in its early history. And that really relies upon the planet having been a slow rotator, as it is today, in its early history as well. That's not well constrained, but it is certainly a possibility. We have done simulations of modern and ancient Mars, but unfortunately without CO2 clouds. Those play some role in relative balance of present-day Mars, not so much in ancient Mars, at least in terms of having, if you want, warm and wet conditions, which some people believe took place in the early history of Mars. And we'll talk a little bit more about that tomorrow. But there have been two recently submitted papers with ROCKE-3D on ancient Mars. One that will be published in JGR Planets, hopefully any day now. We've just submitted all of the referee comments to that paper. And there's another one that has been submitted to Nature Geoscience. We'll see what the referees say about that. But both of those are looking at ancient Mars with warm and wet conditions. And we've also looked at hypothetical Venus-like worlds near M dwarfs. Of course, these are likely candidates that we will find more and more with satellites like TESS. And of course, the Kepler mission. This was a particular Kepler target. This was a paper led by Stephen Kane and collaborators, myself included. I did the simulations for this, where we looked at what kind of world could be supported in this particular system. And then, of course, looking at another nearby exoplanetary system that everyone is interested in, there's the Proxima Centauri B system. And this was led by our co-worker, Tony Del Genio, in 2019. We did a whole range of different atmospheric types to see how the model responded around this very cool M dwarf that the planet is surrounding. And you can see we did some quite different types of atmospheres here, mostly pure CO2 atmospheres and pure N2 atmospheres, but also a mix of atmospheres with very thin atmospheres down to 0.1 bar and atmospheres up to 10 bar. So that tells you some of the capabilities of the model. Some of the other things we've done is looked at shallower oceans versus deeper oceans with this coupled model to see how the world responds to those sort of things. And we've even changed the salinity of the ocean to see how it responds, because it's an unconstrained parameter, of course, but it's something that can be looked at with our model, different sorts of salinities. And that kind of work has been followed up by by people like Stephanie Olson, who took this class a couple years ago, I might add, and successfully has published a couple papers using ROCKE-3D to look at such scenarios. This is another paper that was published, I guess it's been almost 2 years in May now, by Igor Lienov and a few of us in the group, looking at very thin lunar atmospheres. This is a hypothetical scenario where the ancient Mari on the moon could have outgassed significant amounts of water and CO and CO2 and presented itself as a very thin atmosphere that could have allowed water transport to the poles. And we modeled that scenario with this. And Igor has an ongoing project with using the model to look at these kind of atmospheres. Our hope is to get the model down to microbar levels, so you can do extremely thin atmospheres. And Igor will probably talk a little bit more about that tomorrow. That sort of capability is more robust in Planet 2.0. And going forward, we expect to be able to do even more of these kind of super thin collisional atmospheres, at least down the road. Another thing that the model has been used for is looking at obliquity studies. This was a paper led by one of our postdocs, Chris Kalos, back in 2019, showing these different sort of hysteresis plots that were first discovered by some Japanese coworkers and other people around the world using different kinds of models. So you can look at quite distinct obliquities of the model. So that's one of the model's many capabilities. And here you can see also that in a more recent paper that Chris Kalos has published, we have looked at different spin orbit resonances for different installations of the model with different solar types. So you can see in the diagram on the right, the sun at the top, then with about a 5,600 Kelvin surface temperature. And then you can see we go down 4,500, 4,000, all the way down to 2,600 Kelvin. These are M-dwarf type worlds. And you can see how different sorts of installations and different sort of, this sort of spin orbit resonance gives you different kinds of surface temperature patterns on the planet. And another thing that we have initiated the model is geothermal heating. So you can also add different sorts of geothermal heating. You can either add a sort of global geothermal heating of whatever value you want, or you can also apply geothermal heating at the grid scale level, if that's what you want for your particular simulation. And then we've looked at large parameter ensembles. This is just one of the larger ones we've done. There are others that are ongoing. This is a paper I led a few years ago looking at how the global surface temperature changes with different rotation rates and insulations. So each one of these dots in these plots is a full-blown 3D simulation for a particular world. And the different colored lines correspond to different rotation rates. So the day length gets longer for different values here. So 1 is, of course, a present-day Earth day. X002 is a day length that's twice as long as Earth's sidereal day length, all the way up to 256. And you can see sort of a split here between what we call the fast rotators, these very fast rotators in the upper left of the plot, and down to the right, the more slowly rotating regime. And that's all because of the dynamics of the atmosphere changing. This is replicating some work that was done by Jun Yang and collaborators at University of Chicago using the NCAR model. And this is just to suffice to show that more than one 3D model is showing the same sort of behavior. On the left, you see this set of simulations using a very simplified, what we call a mixed layer ocean, or what we call in-house a Q flux equals 0 ocean. So there's no horizontal ocean heat transport in this ocean. It only has some thermodynamic capability, 100-meter deep mixed layer ocean. Whereas on the right, we have a full-blown, fully coupled dynamic ocean. You can see the curves do differ some, but qualitatively they're very similar. So this shows you that having a fully coupled ocean probably gives you a bit more realistic picture, but in a qualitative sense. In this particular set of scenarios, the Q-flux ocean doesn't do too bad a job, actually. And the other advantage of the Q-flux ocean is that it runs much more quickly. It comes into dynamic, it comes into radiative equilibrium much more quickly than the dynamic ocean. If you put a forcing on the ocean and the ocean is, say, 1,000 meters deep, it takes a while for the ocean to come into equilibrium with the atmosphere. Whereas if you have a Q-flux ocean with a 100-meter deep level, it comes into equilibrium much more quickly. So the simulation on the right probably ran around 1/3 or 1/4 as long as the simulations on the right. The simulation on the left ran, sorry, about 1/4 as long as the ones on the right, each one of them. Okay, so why do we tell you about these papers? So as I say here, the fastest and most reliable means to get a new planet running that you're interested in after this tutorial is to find a similar one in one of our previous papers. You can find all of our papers listed on the ADS servers. Um, the thing is that we publish all of our run decks. You'll find out what those mean if you haven't already got some experience from following our installation instructions. You can find the run decks, boundary condition files. Those give the initial conditions for the model and model output for most of our papers online at this particular link below. So for each paper the group publishes, we try to put all of these different aspects of the model up online. So if you want to take one of our models and you want to reproduce it, or you want to take one of our models and change something very slightly, we provide all that information here. And that is something we're going to continue to do going in the forward. And it's something that we have encouraged our fellow GCM modelers to also take into account moving forward. Okay, but there are some caveats, of course, which I've touched on just a little bit. There are a limited number of types of atmospheres, as I say here, and as I say, stellar spectra available. So what kind of spectrum is incident upon the world that you're interested in modeling? And we'll discuss them a bit later, time permitting at some level. Okay, what can it not be used for at the moment? So here, one of the first things I mentioned here is variable atmospheric mass for a mix of constituents, meaning that the mean molecular weight of the atmosphere cannot change through time. That might happen in a scenario, for example, where you have an N2 and CO2, say, mix of an atmosphere, and the CO2 atmosphere starts to condense out on the world. That would change the mean molecular weight of the atmosphere, and the model starts to become invalid in such situations. We have trouble modeling super Earths. Those are related to dynamical issues, which we won't go into too much here. As I said before, where the thin atmosphere approximation is invalid, the model does not work very well. As I said, Titan and mini Neptune type things. I put here super thick oceans with a question mark, but Tony Leboissetier will talk a little bit later about that. We've done some extensions to the model to allow us to do deep ocean worlds. That is not in the production version of the model yet, but we expect that to be pushed eventually as a supplement to Planet 2.0 down the road. There are some limits, of course, in the model itself. As you see here, generally the model is not valid for temperatures over about 400 K. What I mean that is that if you put your star too close to the planet and it heats the atmosphere up too much above 400 K, you'll start to find radiation errors, and the model will most likely bomb, and also not below 100 K. This has to do with the radiation tables that we're using and also some aspects of the dynamics. We do have some problems with really cold planets. This is mostly related to, at least for the dynamic ocean, with the ocean freezing to the bottom. And in a scenario like that, this is for people interested in modeling, say, the outer edge of the habitable zone. The issue with the most ocean freezing to the bottom is that we like to joke that the ocean doesn't like to be squeezed out of existence. And currently the model is not capable of changing surface type. So in theory, what should happen is that if a column fills up with ice, that should be changed into a new land surface type, or surface type that would be, say, ice or land ice. But presently the model is not capable of doing that. We're waiting on our earth science colleagues to implement some changes to allow that to happen. Not exactly sure when that would happen. We're hoping within the next year or two, as there is some interest on the earth side of the house to look at that. There are some issues with very fast spinning planets because of the grid resolution we use. Some of that will be addressed with Planet 2.0 because we're going to have a production version of the model available that goes down to 2 by 2.5 degrees in the horizontal resolution. Currently, right now, the base model is using a 4 by 5 degree. As I mentioned before, mini Neptunes and above are problematic. And remember the acronym, this terribly long acronym that we have, resolving orbital and climate keys of Earth and extraterrestrial environments. We're really talking about terrestrial worlds. One thing to keep in mind is the model does have this South Pole anomaly that many models have. Many models have a North and a South Pole anomaly where If you want to run an aquaplanet, for example, you're forced to put a land point at the South Pole. You can make it of 0 height if you wish. Okay. We do have a code repository, which you all should have had some experience with by now to download the model. And there is some documentation which we continue to work on over time. And as I said, we have an example here of a dynamic ocean run deck, and then one of the Earth parent model run decks that you can pull down. But as again, I said, the best solution if you want to get a model running quickly is to look at one of our previous papers, find something that's similar to what you're interested in, download that from our online repository. There are different snapshots of the model. Of course, we are doing bug fixes to the model or small enhancements to the model over time, and those will show up in these snapshots, which are updated every day. That doesn't mean that we are making changes every day, but there are daily snapshots available. And finally, as I said, the model is very complex. We have a large team that is working on different aspects of the model. Many of our team members work on both this planetary side and the Earth side of the house. So I've listed their names there. Really, the first people you should contact if you have a question about the model or a problem with the model are really myself, Kostas Tsigaridis, and Igor Alienov. But I put these other names there so you know kind of who's working on what. And if it's something that we cannot resolve or we cannot give a satisfactory answer to, we will send those queries on to some of the people listed here who work on these different aspects of the model. The model, as I said, is very complex. All these different components of the model have small teams working on them, and these are the leads of most of those teams. Okay, so at this stage, I think I'm going to let Kostas Tsigaridis take over the slideshow. So Kostas, do you want to go ahead and show the slides yourself at this point?
I think it will be pretty obvious to when you will have to advance the slides, if that's okay with you.
I can go ahead and advance them, no problem.
Yeah. So this slide is only listing ways that you might see the model being named at different venues. So if you are doing the Earth side of the model, then you have the E part in the model name, and then depending on SNP 5 or SNP 6, you have different versions. And then in the ROCKE-3D part, we have Planet 1.0 that we're discussing here, and Planet 2.0 that we are writing the paper right now. And we also have different ways to simulate the atmosphere in terms of composition. So either non-interactive, which is what we call NINT, and this is it stands for non-interactive, obviously, and you simply prescribe greenhouse gases, and then they can change with time if you want, but the typical thing for a ROCKE-3D simulation is that they just stay constant throughout the simulation. And then we have different aerosol components that we can turn on. We call them OMA and matrix. And I can tell you a few more details in the next slide, in which we essentially simulate the aerosols in a simplified way or in a more complex way. Go next, please. So there is some more terminology, which is now hardcore in terms of the model. So if you have already downloaded the model and compiled it, so you have probably seen all of those things. First of all, the .model ERC file is where you hold your local configuration, where you describe your environment, where you have your libraries, where you have your executables and stuff like that, and when you have your input and output directories. I believe everybody looked at that, so you should already be familiar with it. Then we have the model repository. For example, here we assume that it is under your home directory, and it's called model E2_planet_1.0. This is where the Git repository lives, and all the source code and supporting material is in. We have the templates subdirectory in there, which contains some sample rundex that we have there available for you, and we will be discussing about 2 or 3 of them in this tutorial. It's really important to remember that the template rundex and the rundex that you use for your experiments is not the same thing. A template is not meant to be used directly. So you do not copy a template directory from that directory and into your DEX and then you do work. You have to run a specific command that you all have run, the make rundex. So the template rundex contains instructions on how to construct a proper rundex for your experiments. And you do not modify those templates unless you are creating something completely new that you want to make available to others. In general, you take a template or an older rundex from someone else, and then, for example, our website, and then you put it in your DEX directory and you make changes there. So all the rundex that you're having during your experiments are into the DEX directory, and you should already have your first one sitting in there. And the source code of the model is into the model subdirectory, and that one also contains some subdirectories itself. Okay. So then we have the shared input files, which are defined in their location can be user specific, and it is defined in the .model ERC file under GCM search path. And every time you provide in your rundex a file name as input, and you do not start it with a /, this tells the model to go into the default input files directory and find the file in there. You can have subdirectory structure, as you will see in the rundex later. But the important thing is that you do not start with the /. You give a relative path compared to the GCM search path that you have in your .model ERC. If you have input files that are somewhere else, just because they are testing, they are not for production, or for whatever other reason, you need to provide to the rundex the full path, starting with a /. And then the output files are saved in the save disk directory as defined in your .model ERC. And so every model simulation you're doing based on the rundex is creating a subdirectory with the same rundex name except the .r extension into the save disk, and also creates a soft link into your DEX directory by using the same run ID. So the save disk contains the physical files, but you can easily access them from your DEX directory. So you don't have to go back and forth across in longer distances in your directory tree. You can simply see the output from DEX through the soft link. Next, please. Then inside the rundex, I guess that I believe that people were curious to open the rundex and see how it looks like. In general, it's a very long text document, but the main structure is the bullets that you see here. There is one object modules that contains the list of Fortran files to be compiled. It contains essentially all the file names, excluding the extension .f or .f90, that you want compiled from the model directory. If you want to compile subdirectories that contain the model components, you need to list them under the components part. And you don't list all the files in the components, you only list the component names. So in essence, files to be compiled are the file name, the Fortran file names that are in the model directory, and the components are the subdirectories that are in the model directory. And every component has its own make file. And that make file can take options that you list under component options. We will see those things in the rundex as a little bit later, I guess, or maybe even tomorrow. But you can go ahead and open those this rundeck that you created yourself and see where these things are being listed and how the syntax is defined there. Then we have a very long block that is the data input files. I just described you how you define the input files, how to find them in the file system, and they can be literally anything. Can be emissions, can be boundary conditions, can be any external forcing, like something that varies with time. For example, if solar variability changes with whatever reason, you can have that there. It can be anything that you externally provide into the model. And then for several of those files can be used as templates for your own custom input files, or you can create your own reading in the model if you are providing with some input that is too exotic to that we took care of it already. Then we have the name and name list, which is essentially saying the run name or run ID, as we also say it. And then it provides some one-line comment that ends up also in the netcdf output. So it's a good practice to put some comment in that line that defines your experiment briefly, and then that ends up in all your netcdf output, and you can always remember what exactly this run ID is doing. And then there is another very long list of parameters in the rundeck. It starts in the parameters line and ends in the end parameters line. And it includes things like that we are providing externally to the model as runtime parameters. Think of it as variables in Fortran. When you say a equals 5 in Fortran, there is a way for the model to get that value from the rundeck, or use a default if it is not present in the rundeck. Not every variable in the code can be accessible by this method. Only the ones that we have implemented the code to do that. But it is very easy to add your own. And there are hundreds probably of examples in the model on how to take different types of variables, whether they are integers, floating points, arrays, strings, you name it, and or booleans. And then you can just plug some similar code, and then you can control the model like this. The advantage of doing that is that if you want to do a sensitivity study, let's say you have some variable that is uncertain and you want to play with it, and you want to do 5 different simulations with 5 different values. The simple way is to go in the code, change the value, compile, run, and then change the value, compile, run the other flavor, etc. But that way you do not have control from the rundeck on the actual experiment, because you have to make changes in the code. There are 2 ways to go around it. One way is you create more Fortran files that change the values, and then you list them in the files to be compiled at the very top. And you do that for complex things, like you change an equation, or you change more than 1 lines, or a value or a variable. But for simple things, as I said, you just want to test the value of one simple parameter and how that affects things. You list it into the parameters section. You have 5 rundecks with 5 different values there. You make sure that the code understands this and knows how to read it and how to use it, and then you run it. And then there are no changes needed in the model. There is no recompilation needed practically. You only need to create the new rundeck and run it. And then another very important thing that we will be discussing in the following slides is that this input Z block, it is 3 lines at the very bottom of the rundeck that control 3 things. When the model starts in model years, model time, when the model ends in model time, and how exactly it starts. Whether it starts from some standard conditions, the initial conditions, whether it is continuing a simulation that we already have, these things. Go next, please. So in terms of the key template rundex that you care about, these are the four listed here are the ones. Note that they all have a P, which means that they are for the planetary flavor of our model. There will be plenty of other templates in the templates directory. Do not assume that you know exactly what they do and you start using them. Please contact us first. So from the ones that start with P, then you see that here they all contain the uppercase S, which means that they are running with the Socrates radiation. Then before the S, there might be a number, either 1 or 4. It is 1 for the coupled ocean and 4 for the Q-flux or the prescribed SSTs. This number doesn't really mean anything to you, so it's you just need to know that there is a number there that has some meaning to us only. And then there is the M40, which is the resolution. M means 4 degrees in latitude and 5 degrees in longitude, and 40 means 40 vertical layers. And Mars also has the M40 resolution. And then there is the lowercase o for dynamic ocean, the lowercase q for the Q-flux ocean, and no letter between the S and the M for the prescribed SSTs. For Planet 2.0, we have many more options, and then we will be discussing those probably in the tutorial of next year. Again, I want to stress out that you should never confuse the template with a working run deck. You do not go in the templates directory and copy that in your decks. You run the command that we have in our instructions, make run deck src equals, etc. Next, please. So the next things that we will be doing is go into a detailed analysis of this run deck that you see here. We can compare the differences between the Q-flux and the coupled ocean run decks to see how they differ. And then we can even compare the coupled ocean with the Mars template, which is a desert planet. And it has a lot of differences. I mean, it will be major differences. And there is a link here that we have the complete list of variables that we want to we have in the model. It is very detailed and exhaustive, and we can but you can find some documentation there. Most of it can be found also in the model via grep if you know what to search for, but it's a simple way to find all the variables that are available. I think that this is a good place to take a break, so I'll pass this to Mike.
Okay, great. Yeah, we'll take a small break here, a 15-minute break. And if you want to ask a question in the chat, that's fine if we stick around. Otherwise, enjoy your time off. We'll start up again in, well, I guess 15, 20 minutes. Okay, thanks.